We're thrilled to be coming direct to you from our various locations across the world today. And understanding that COVID has changed the way we all work, we're thrilled to bring you a deeper insight into a topic that's very dear to us all in Heatex, and that is indoor air quality. Also, throughout the presentation, we're going to try to shed some extra light on a topic that I know has been asked in many meetings across the year of 2020, and that's a topic of indoor air leakage within rotary heat exchangers. So as we go ahead, we aim for the webinar to last around 40 minutes. And throughout the course of the webinar, there'll be an opportunity to post questions in the question box that you see on the screen. Gustav, my colleague, will collate all of those questions, and when we get towards the end of the webinar, we'll try to answer as many questions as is possible. So please feel free to ask any questions as we go through the presentation. The agenda for today, we're going to start with indoor air quality and ventilation. Then we'll move on to an introduction into Heatex. So some of you may be joining us today for the first time, and some of you may have known and worked with us for many years. But for the benefit of those joining us for the first time today, we're going to give a very brief overview of who we are and what we do. Then we'll go on to a basic look into leakage within rotary heat exchangers. And when we say basic, this is a very expansive topic and could easily fill perhaps 3 hours of a webinar. So what we aim to do is try to break this into smaller chunks so that we'll have a basic, and then in later volumes, if everybody approves, we'll have an intermediate and then a more advanced overview into leakage within rotary heat exchangers. And then we'll go to a question and answer session towards the end. So, presenters for today's webinar is yours truly. My name's Paul Rigby. I'm the area sales manager for United Kingdom, Ireland, Spain, Russia, Ukraine, and South Africa. I've been in the HVAC industry now for 20 years, which is almost my entire career. And I'm in my 6th year at Heatex. Now, the eagle-eyed people amongst the audience today will know that that hasn't been 6 consecutive years, but I'm thrilled to be back here in Heatex in such a good company like this as well. But also joining us on today's webinar is my colleague and good friend, Mr. Gustav Sassner. Over to you, Gustav.
Thanks, Paul. So my name is Gustav Sassner. I work here at Heatex as application engineer, focusing on ventilation system and projects. But I'm also supporting our offering in data center cooling. I've been working with heat exchangers the last 15 years, and the last 4 years has been with Heatex.
Okay, thank you, Gustav. So, for sure, there'll be some of you joining us today that have known and worked with Heatex for a long time, but for some of you, they'll be joining us for the first time here. So what we'd like to do here is just to give you a really brief overview, single slide, of who we are in Heatex and why we're motivated behind making the world a better place in terms of indoor air quality and sustainable energy as well. So, for the need for a sustainable future is now, and we need to try and make it a green, much better bounce back from the recent troubles we've had across the world as part of the pandemic. So we have an almost a mission statement in Heatex, which is to cut fossil fuel consumption and protect our environment for future generations through the development of energy-saving products and solutions. And we aim to do this in 3 different ways. So we look to reduce the impact of energy consumption through our air-to-air heat exchangers, which are in HVAC systems. Then we also focus towards protecting sensible electronic equipment in our thermal management systems, such as solar energy inverter systems and some things like this. And then also one of our new faster growing product lines is generator cooling for wind turbines as well. So we're fundamentally a Swedish company, and our HQ is based in Malmö in Sweden. We were founded in the 60s, but it wasn't until the late 80s where we were incorporated into Heatex AB and where our growth to become a market leader really started. After this, we formed Heatex Incorporated in the United States, and following from that, we also formed Heatex Shanghai to look after our Asia Pacific markets. And this has really helped us to cement our place as a market leader in air-to-air heat exchangers. So we're going to start this topic on IAQ and ventilation with looking at how some new systems like smart technology combined with existing systems like we have with our air-to-air heat exchangers can help to create a much healthier lived in and worked in environment for us all. So our aim during this is to show that there's a perfect harmony and balance that can be achieved between the renewable technology we all know and work with today, and then the new and emerging smart technology that is going to help us to really break down this cycle between creating pollution and bringing this pollution into our buildings and lived in spaces. So it's no surprise to anybody that really these days that the air pollution outside of our buildings and office blocks and houses and apartments is quickly becoming the pollution that's contained within our buildings at this point. And this rising air pollution is really driving a fundamental change towards our views towards indoor air quality. And to underline how important this is why we have things like the Paris Climate Agreement, which has been adopted by over 195 countries across the world. So the smart technology is evolving now and evolving very quickly with the use of the internet. So there's a system available now and implemented in some people's technologies these days, which can talk to our HVAC systems in real time. And is smart technology in that respect. So the system called Breezometer works by having a number of different pollution monitors stationed in different cities and different parts of the world, which can feed information back in real time to control equipment that's linked to air handling units. So as you see in the top right-hand corner here, you can see that on this particular day that Poland was having a pretty tough day for air pollution. So what that information can then do is we can take this information into our HVAC systems, and in the times before pandemics and hopefully soon after pandemics, will allow our HVAC systems to check sensors that are contained within our spaces to see if the air inside our space is better than the air outside. Obviously, after pandemics, that then gives us an opportunity to say, hey, okay, the air outside is pretty bad today, so let's focus on recirculating the air that's within our spaces. So this sort of new technology is really going to help us to monitor the quality of the air in the building and replace it only when it's good enough standard outside to be beneficial to the occupants within the building. So as engineers, manufacturers and designers, the responsibility for indoor air quality lays with all of us. And really, if we look at the COVID pandemic, it has been a catalyst for us to focus a little bit more on indoor air quality. And with the new smart technology that's realizable and already implemented in some systems, we're ready to go with this now. So it means that we can start to think in a smarter way as we go forward. But really, it all boils down to a rule of three, which is something that everybody watching today shares. And that is the fact that an average human being can last up to 3 weeks without food, can last around 3 days without water. But when it comes to air, 3 minutes. And every second is counting with this. So to avoid irreversible brain damage, we have to be careful of the air that we're breathing. And we also have to think a little bit about the trickle-down effects of this. If we're depleting the air that we're breathing and polluting it, and we're doing this over a long period of time, the consequences of that could be quite serious in many years to come. So now is the time to really to make some changes and to understand how this is affecting us all. But there's other steps that we can take with improving indoor air quality that are both low cost and perhaps can give good results even in existing applications that we have. So things like improved ventilation rates. Now, during the early stages of the pandemic and still today, the guidance is really to increase the amount of outdoor fresh air that we bring into the spaces. So simply improving and increasing the amount of fresh air we're putting into buildings is certainly going to help matters in that respect. Then there's things like correct and timely checks of HVAC system. So making sure all the seals and everything are in good working order, the alignment of the rotor is correct, and there's no breaks in the seal. Better filtration. So filter technology is coming on a long way these days with the invention of HEPA filters and certain things like this. So making sure that we're getting a good level of filtration on the air that we're bringing in, but also making sure that the filters are checked, cleaned, replaced wherever necessary, and trying to avoid any filter leakage, filter bypass leakage. Then there's things like reducing the amount of volatile organic compounds within our buildings. So things like plastics and certain things like this that give off vapors and odors and chemicals over time as well. But more pertinently, recently in the COVID pandemic, we're also using a lot of chemicals these days to clean spaces a lot more efficiently. So it's really making sure that the space is adequately ventilated when we're using these types of cleaning materials within the space. So then there's also the issue of air purifiers and UV filtration systems. So unless you've been living under a rock for the last 12 months, you'll see that there's a huge number of air purifiers and UV filtration systems on the market. Now, these are really good. The technology behind this is tried, tested, and extremely effective. But even the World Health Organization states in their roadmap to improve indoor ventilation in the context of COVID-19 that it's not really a replacement for a good level of ventilation. We still need good levels of ventilation because the air purifiers and UV filtration systems are merely cleaning the air. We still need the air, first of all. So it shouldn't be overlooked that would replace having a good ventilation strategy in situ. So when we start to look at indoor air quality, smart technology systems, and trying to look at also the products that we have existing, so heat exchangers, this is where we try to work towards a harmony of new and existing technology. So if we take, for example, a building in Stockholm in winter and then a building in Dubai in summer, we have a huge temperature differences between there. So whenever we increase the amount of outdoor air that we're putting into these spaces, it requires an additional component. So in Stockholm in winter, it's going to require some additional heating, whereas in Dubai in the summertime, it's going to require additional cooling. So those types of processes that we're applying to these air are creating pollution at some point, unless they're coming from sustainable sources. So really, by using heat exchangers of any type in that respect, we're helping to renew that energy and making that delta between the amount of energy we would need to use without that product and the energy that we're actually using with the use of that product. We're making that much smaller. And when we think of this in a huge cycle, actually this goes quite a long way, because if we're using a lot of energy to create heat or to cool down air, and that energy is not renewable, at that point we're actually creating and adding to the pollution that's outside anyway. So really, by using some form of heat exchanger, we're really starting to help to lower the outdoor problem by also fixing and correcting the indoor problem. So fresh, clean air, good for indoor air quality, leads to leakage concerns. And what we aim to do in this section is really to sort of quell any fears around leakage in rotary heat exchanger or even plate heat exchanger basics. And by following good practices and good design, it's possible to ensure that we get a good level of indoor air quality whilst having a good level of energy efficiency as well. But again, as I mentioned at the start, it's important to understand that leakage is an incredibly expansive topic. Some excellent documentation from Eurovent's been released recently, detailing all the different steps you can take within air handling units to reduce leakage at that point. So whilst we look here to try and cover the basics, there is a lot of scope here to have further modules on this, to take it to an intermediate level, all the way to an advanced level on leakage. But I had an old lecturer a long time ago that said that the head can only take what the backside can handle. So this is why we like to try and break this down into smaller chunks. But one thing that's important to understand is that as we look to improve indoor air quality, sometimes we need to make some compromises into energy efficiency. So if we're increasing the outdoor airflows or flow of fresh air into the building, that's obviously going to use more energy. But it's our job as professionals and engineers to strike that perfect balance between having the most energy efficient system whilst creating a good level of indoor air quality. So leakage has never been ignored previously, but perhaps not focused on as intensely as in the times we've had in the last 12 months with the COVID pandemic. Leakage has always traditionally been about smell and pollutants in the air. But for the sake of indoor air quality, we need to look to minimize leakage as much as possible. A good colleague of mine last year, just after the pandemic started, we started to look into leakage around units, and he stated to me at that time that the COVID pandemic was sent out to teach us to design systems properly and to take everything into account. And I happen to agree with him on that, and it's a point that's stuck with me ever since. So when we look at indoor air quality, we're really looking to try and remove virus and disease such as coronavirus, influenza, rhinovirus, which is the common cold, which I'm just recovering from after last weekend, and also any other airborne viruses as well. So indoor air quality is really going to help us to try and get these under control. Then there's things like dust and man-made fibers that are in the natural environment that we're all working and living in. Skin particles, other bioeffluents, all of those nice things like that as well. So looking to try and remove all of those. And then for hay fever sufferers across the world, and I know I suffer with this sometimes in the spring, we're looking to try and remove pollen and other naturally occurring contaminants from the airflows as well. But when we start to look at the viruses and coronavirus and certain things like that, investigations have been done by REVA that point out a very low risk of something like coronavirus being transferred through rotary heat exchangers and other heat exchangers. So the quote that they have currently is that it's been shown that rotary heat exchangers, which are properly constructed, installed and maintained, have almost zero transfer of particle-bound pollutants, including airborne bacteria, viruses, and fungi. And the transfer is limited to gaseous pollutants such as tobacco smoke and other smells. There is no evidence that virus-laden particles larger than 0.2 micrometers would be transferred across the wheel. And that ties in with a lot of studies that we make as well within Heatex, that the risk of leakage, if done in such a correct way, is going to be so small that it would be a very serious case if that was to ever happen with a rotor. So this is more of an opportunity really just to quell any fears that so far the evidence looks very unlikely that anything would ever be transferred through a rotor. So here we're going to take a look at what leakage is. We're going to take a basic but common IAQ design and show the relatability between the common phrases and terms used. So we'll start with OACF, and this is outdoor air correction factor, and is of course a result of leakage, but perhaps it's more a loss of capacity. Then we move on to the exhaust air transfer ratio, which on the other hand is leakage of used air that we don't want back into the building. Then there's something called pull-through fans, or a pulling fan as some people may call it, and this is often the preferred choice for air handling units. So this is fans that are pulling the air from the space and discharging it either outside or pushing it back into the building at that point. Then there's blow-through fans, or a pushing fan as some people may call it, which is the same principle as the pulling fan, but obviously in the reverse way. So now we'll take a quick look at the purge sector function, and that is this small triangle that you see on the screen here. And really, I think the use of purge sectors is becoming more commonplace in everybody's air handling unit designs these days. And whilst I think they are becoming commonplace, I also feel that not everybody understands how these work. So to talk through the diagram you see here on screen, the idea of a purge sector is to try and reduce EATR through something called rotation-induced transfer, or carryover, as some people may know. So if we look at the bottom right of the diagram, we see the return air. If we change the word air to water, and we have it going through the heat exchanger, as the heat exchanger turns around into the opposing airflow, we wouldn't expect that heat exchanger to be completely dry by the time it gets to the opposing airflow. So again, go back and switch the word water for air, and you will see that within the matrix of these rotors, as you see at the very top of the screen here, there's very small channels, and those small channels can contain air or contaminants in there from the exhaust air side. So really the idea of the purge sector is to have a very short, sharp blast of the fresh outdoor air before the rotor goes through fully into the outdoor air section and the heat transfer occurs. So that's going to help to reduce any carryover or rotation-induced transfer, and that's essentially the main function of the purge. But one thing that's sort of important to understand is that there will be a very small loss of supply airflow by conducting that way of thinking. So then we go and we look at perimeter sealing. Now, this is the seal that fits around the edges of the rotor and is in contact with the face of the rotor itself. This can often be a brush seal like you see on the screen, or in some cases a PU, imitation leather type seal. And the idea of this is to try and create as tight a gap, as tight a seal between the rotating matrix itself and the casing. So when we look at the perimeter seals, these are items that we need to check, and we should be checking during good maintenance procedures of the rotor itself, because these are, it's a fixed component that's moving against a rotating component. So after time, these will wear down at some point. So it's an area in maintenance we should really focus on. Then we have the middle beam and the sealing. Now, the middle beam also has a seal on to try and help minimize any leakage from cross-deck transfer. So in this example, this would be a top and bottom deck example. So you would have one airflow above, one airflow below. And the idea of this middle beam sealing is to try and create as tight a seal between those two separate airflows as possible. Now, this middle beam, obviously, in this instance is horizontal. So in some configurations, it might be that you have a side-by-side airflow configuration, and that middle beam there would then go vertical at that point, but it would still have the same sealing on there, and the same purge sector ideas would still apply to this as well. So here we're going to take a basic and common IAQ design and then show the areas that should be considered when we start to think about leakage in air handling units and rotors. So starting with the rotation-induced transfer or carryover section, as we mentioned on the previous slide, this is the any contaminants in the air that's moved through into the opposing airflow. So that's a potential area for leakage. Then we have the leakage around the cases, which we aim to eliminate as much as possible through the perimeter sealing of the cases. Then we have the outdoor air correction factor on the left-hand side and the EATR on the right-hand side, which is the exhaust air transfer ratio. But there's also the leakage of the entire case of the air handling unit to take into consideration. So when we say leakage of the case and how critical that could be, if we had a plant room with 4 air handling units in the plant room, and let's say, for example, it's a hospital and one of the air handling units is taking extract air from the mortuary or some other place that's critical within the building, if the case of the air handling unit is leaking, then there is a chance that some of the other units close by could take that air in from that space as well. So there's positive and negative leakage that's possible from the casing of the AHU. And I know within the Eurovent guidance that they've been doing a lot of work over the last 5 or 10 years at least to try to improve that leakage standard. So with different leakage levels that are permissible. So when we start to look at the units as a whole, we have to consider every single component, the space where they're in, and everything else that goes with that as well. So here we take a brief look at the purge sectors. So on the top 4 pictures here, you can see that these are horizontal units. So this would be a typical configuration like we've seen already, where the supply air and exhaust air would be on opposing decks. And here you can see that the airflow is signified by the correct colored arrows there, and you see the different orientation of the purge sectors. So on the bottom 4 images, you also see the same, but with the vertical configuration. And the principle is exactly the same. We're just changing the airflow configuration from top to bottom to be side by side at that particular point. But one question that gets asked quite a lot is about the purge sectors, and why do we have different size purge sectors and different angles, and how does that work? So if we take a standard condensation unit, something that's just recovering sensible energy, in Heatex we have a suggested rotations per minute of that heat exchanger at 12 RPM. So you'll see at 12 RPM, we suggest 2 3.5 degree angle purge sectors. So when we talk about 2, it's 1 purge angle above the divider beam and 1 purge angle below. And we use the angle of 3.5 degrees since that gives us a coverage of the casing that's not fixed to the diameter of the rotor. So as the rotor gets bigger, then obviously the purge sector gets a little bit bigger with it as well. So then you have different rotation speeds. So when we start to look at 17 rotations per minute, this would be something like a hybrid unit, which is recovering a little bit of sensible, little bit of latent heat, but it needs to run a little bit quicker to keep up with that. And because it's rotating quicker, we need to have a slightly bigger purge angle on there to make sure that we get the full use of the rotation and the purge. And then we go all the way through to 25 RPMs a minute, which would be something like a 3 angstrom molecular sieve type rotor. And again, because the rotation is so fast, we need to have much bigger angles of purge. And the 2 part again comes from the top and the bottom of the divider beam, whether that's vertical or horizontal. So when we look at the official terminology, OACF value. So OACF, in the best of worlds, the OACF should be 1. This means no loss of supply air volume. But in order to avoid leakage in the EATR side, it is better to have an OACF slightly above 1. Now, not forgetting that EATR is the critical side of the leakage, especially with pandemics. So this is the leakage of potentially contaminated air from the space into the fresh air supply. So correct configuration of airflow, fan placement, and purge can reach Eurovent levels of 0%. Now, 0% is a term that's used on a lot of data sheets and certain things like that. It's never going to be absolutely 0, but it means that with the rounding up that you can do of percentages, rounding up, rounding down, it means that it's a value of no higher than 0.5. So whilst it says 0%, it is to be taken into consideration that it's not going to be 0. There needs to be some sort of clarification to that. Now across the world, actually, across Europe, there is no guidance to say that there's a maximum amount of EATR from a European level. Different states and different building codes within different states will have different levels of what is acceptable in terms of EATR. For example, Poland has a maximum EATR level of 5% for rotary heat exchangers, and I think it's 0.25% for plate heat exchangers. So whilst there's no overriding guidance across the whole of Europe right now, that guidance is being looked at in terms of EATR and OACF under EN 308 across the whole of Europe to potentially standardize leakage levels within EATR and OACF. So what's the best practice? We in Heatex, we've spent many years looking into how changes within AHU construction can impact upon our products. And we can confidently suggest the best practices here as a good guide to reducing leakage within rotors. So if we take the top left-hand corner, the best configuration we can find is to have pull-through air through the units, a positive pressure differential, having fans crossed at opposite sides of the units with a purge sector used, and the EATR on the data sheet is likely to be close to 0%. The next best after that is identical, except without the purge sector, and that should be possible to reach an EATR level of 5% or perhaps below. What we don't recommend, though, is when we're having both a pushing fan on the supply and a pulling fan on the opposite flow. And in order to minimize EATR, a pushing fan is always going to be best, but it's sadly not practical since that'd give a very high OACF. So if we have a system like we have on the not recommended section here, the supply fan is pulling, the exhaust fan is pushing, it creates a negative pressure. And it doesn't matter whether we add a purge sector to this or not, it's not going to help this situation. So when we look at this differential pressure impact on how effective the purge sector is, we see that between 0 and 200 pascals differential pressure has a low impact on the purge sector. Whereas we get a much better impact on the purge sector from a differential pressure that's between 200 and 500 pascals, which means that the purge sector is functioning correctly. And as I mentioned in the earlier slides, there is an excellent document from Eurovent right now that explains something new called throttling. So we've seen that purge sectors and positive pressure is preferred to reduce leakage, but how can we improve situations that exist currently within buildings? And this is where throttling comes in. So when we start to look at an overall system pressure of a unit, if we look from the top deck at the right-hand side, you can see we have 200 pascals of resistance coming in from the building through the ductwork and everything that goes through there. You can see that we have this damper section, which is half open, half closed at that point, which we're using a figure and saying that's increasing the pressure differential to 270 pascals. Sorry, the increase in the pressure to 270 pascals. Then the air flows across the rotor, which adds an additional 100 pascals of pressure drop. So we're left with negative 370 pascals on the exhaust air side. Obviously, we hit the fan, and then that goes into positive pressure. Looking from the bottom deck left, you can see that we have perhaps 50 pascals of resistance on filters coming into the unit. Then we have the throttling damper on the bottom deck, which is fully open. Even though it's fully open, the blades are going to be into the airflow, so there's going to be a little bit of pressure increase as a result of those blades. But you can see here now that we've got this potential to modulate the differential pressure between the exhaust air side and the outdoor air side on the left-hand side of the unit. So we can very accurately control the pressure differential between those points. So we can open a damper to create a little bit more pressure if we need this additional pressure drop, or we can, close the damper if we need that additional pressure drop, or we can open the damper if we have too much pressure in there as well. So that's really how throttling works. And throttling is going to help us to reduce any leakage in these systems as well. But again, it does have a slight impact on perhaps energy efficiency, because anywhere where we increase pressure, we increase the amount of energy that's required to move that air across the system. So, I mean, if you're a Heatex Select regular, which is our selection program, you'll know we have a huge range of different drive options available within our software, but not all of these drive types are created equally. Some drive types have a smart new function in there to help to reduce this carryover or rotation-induced transfer. And to explain what we mean by this is that the controller you see on the screen right now, if we have a building that's just using a hypothetical figure of 10,000 meters cubed an hour at 100% capacity, if through the day people leave and the volume is not required and the unit goes down to 70% of volume, we have the capacity and the potential from that unit to send a message to our controller to say, hey, okay, we're putting less air through the building, so let's reduce this rotations per minute to ensure that we don't get an excess of rotation-induced transfer or carryover. So this is a system that's been within our controllers now for around 3 years since we made a change across to this particular supplier. So that technology is already there and is existing, but not many people know or are aware of that and the functions and the additional benefits that you can get from that. So really this was just to explain that that system is possible and it is realizable today and has been maybe perhaps in existing installs as well. So it's always good to finish a technical session with a quick recap over the points that we've covered so far, and understanding that this is the base level entry, layman's terms way of explaining things. It's always good to have pull-through fans in almost all scenarios are going to help with leakage across those decks and divider beams in the units. Effective use of purge sectors and trying to ensure purge sectors are fitted in the correct orientation, the correct positioning, and that the differential pressure is at a suitable level to make the best use of those. Consider the seals. Sadly, I know through many years of working with heat exchangers, the number of calls we get to replace seals is actually quite low. But they are a perishable item as well, and over time they will wear down. So start to look a little bit more at the seals on the rotors and the alignment. If you can see gaps in the alignment, then you know that the seal is not working at that particular point. So it's a good chance to change and to check the alignment of the rotor. So again, corrective maintenance, these regular checks on sealing systems and rotor alignment. Control and demand settings, as we saw in the last slide. Consider using a controller or a unit where you have that ability and function to modulate the rotation of the rotor depending on the various air volume settings. And then the differential pressure, which is not to be overlooked, and it has a much higher effect than you might think. So considering throttling on existing units, and also taking into account the pressure through the ductwork of existing buildings and new design buildings to try and negate the need to use throttling in some cases just through the ductwork designs. But it's pointless to look at the air handling unit and spend all of this time trying to make it as tight as possible if we have duct-to-duct leakage further down the system, because we could be getting leakage across sides without realizing it in the rotor. The rotor and the unit could be as tight as possible, but if we're getting duct-to-duct leakage somewhere down the system that we can't see by standing and looking at the air handling unit, then we're kind of undoing all of the work that we're spending with the air handling unit as a whole. So, of course, there's going to be some environments where rotary heat exchangers are just not going to be applicable. And those are situations like medical situations. I know in the UK, we have the HTMO3 compliance, and rotors are not suggested within that product. But we do in Heatex have a tried and tested product called the H2, which is a plate heat exchanger. And it's still possible to get up to a level of 80% thermal efficiency with this unit, which will meet all the current regulations and guidelines as EU 1253/2014 or ERP 2018, as some people may know. With this type of heat exchanger, it has a very low leakage as standard, but in Heatex, we can also do additional closed plate cutting edges, so we can get it as close to zero as is physically possible out of any kind of heat exchanger. So it's definitely a product that's worth considering if you're working in tight spaces where you need zero leakage or as close to zero as possible. So we're lucky in Heatex to have a very strong and knowledgeable team of specialists located in every corner of the world. So we're never so far away from valued customers and specifiers wherever in the world. And all of these handsome and beautiful people you see on the screen, our plan is after the webinar today, for all people who have attended, we'll send out an email with all the contact details of everybody you see on screen here. So please always feel free to reach out to these people if there's any questions that you've got, or you'd like to hear some more about Heatex products or leakage or anything, then please feel free to get in touch with those. Alternatively, myself and Gustav, our details are still within this webinar as well, and will be on the email that we send out at the end. So feel free to contact us to discuss any issues that you might have or things you'd like to know. So I really hope you've enjoyed that sort of technical section of the webinar, and I'd urge you to stay connected for upcoming webinars, and also to reach out and let us know what you thought of today, because it's definitely something we'd like to try and keep on doing in Heatex, and to try and cover some issues that perhaps people have questions with. As always, you can go to heatex.com and sign up for the newsletter as well, where all new products and software updates and everything else we communicate as frequently as possible. We also have a YouTube channel now, so head across to the YouTube channel, click on the subscribe button and hit the bell icon, and whenever we make new uploads, which we're planning on doing quite a lot more over the next year, so self-help videos and troubleshooting videos as well, whenever we make a new upload, you'll get a notification to your device saying that, hey, Heatex has released a new video and do you want to see it? We also have a great LinkedIn page as well, which also shows some of the different technologies that we work with, like the solar inverters and the wind turbines and all of the new products. And we often launch some punchy articles on there to start conversations amongst professionals in our industry. And now we will move across to the question and answer session. I'm very appreciative that you've allowed me to wax lyrical on this topic for the last 40 minutes. So now it's your turn to ask any questions to myself and my colleague Gustav that we might not have covered since the webinar began. You can post any questions in the chat, and we have a list of the questions which we'll try to go through. So over to you, Gustav, whilst I take a long-needed glass of water. So.
Thank you, Paul. Well, it seems like you've done a very good job, Paul, presenting this topic. Feel free to ask any questions, because, yeah, currently there's no one that had any questions, which is strange, but now we get one here.
This either means we've done such a good job, or or people are just not talking today.
Yeah. So, hi team, thanks for the overview. Do you also have best practice for IAQs utilizing two rotor heat exchangers, for example, sensible and latent rotors combinations? Well, not in terms of leakage you would have. Let's see, we do in our Heatex Select online tool have a double rotor functionality where you can calculate, and you can also calculate with a intermediate cooling coil. Leakages is handled there as we do for calculations for single rotors as well. So that's how it's handled today.
Yeah, so the documentation you'll see will be very similar, but obviously when we're taking two rotors into account, then we have to consider more or less the similar principles that we've just outlined here. So,
yes, Michael, did you have any question?
I think we just did such a good job here. Okay, would anybody like to suggest anything for any future upcoming editions of webinars if you've enjoyed today's webinar? So please feel free to post any topics up as well, and we could discuss those as well at some point. So thank you, Evrim. I'm glad you enjoyed it as well. Okay. So there is an opportunity to follow up after the webinar if there's there's some more questions coming in here. There will be an opportunity to follow up after the webinar as well with any questions if something should come to light afterwards. But I think we have a question here from Evrim, Gustav.
Yeah, he's writing, we need a high efficiency rotor selection with low pressure drops. Yeah, well, we have a range called Model E, which is our standard commercial range, and for those we can reach a very high efficiency, plus 80% without, in most cases, and we have a recommended pressure drop between 100 and 200 pascals to get a good function out of the rotor. So I hope that covers the need you have.
250 millimeter section length units. Okay, when you're talking, Evrim, about the section length units, you mean the depth of the rotor. You need it to be no bigger than 250 millimeters. Is that correct? If that is correct, then by all means, I'm assuming, and please don't shoot me down for this, I'm assuming you're based in Turkey. So I will speak with Burak, who is our wonderful new area sales manager for the Turkish region. I'm quite sure there is something that can be done on this with 250 millimeter section length. It's not impossible. Certainly our rotor as a standard is 200 millimeters in depth. And when we look at the standard casings, depending on the diameter of the rotor, it varies between 297 millimeters and 316 millimeters. But I know that there has been examples in different cases that we've done for different customers before where that's a little bit shallower. So I will speak with Burak after today's webinar, and I'll ask him to get in touch with you as well. So thank you for the question.
We had another question regarding prediction in our software with OICF and EATR depending on differential pressure, and there is an input possibility. The default value is always 250 Pascal positive pressure differential, but you can modify that between 0 and 600, which is the maximum that we recommend. So you can modify that, and you should see an impact on OICF. And yep,
exactly. Generally speaking, wherever you're going through our software, if you see a little cog or a little question mark somewhere, if you click on that, it often brings up a new different options to make different selections around as well. So it's certainly worth playing around with the software in that respect, because there's different things like you can adjust the altitude of where the units are located and many other different parameters. Yes, we can send a PDF file of the presentation. No problems at all, Michael. We will also, so I should mention this also as well, we will upload the webinar today onto the YouTube channel as well, so that if you'd like to go through and to hear the questions again or to have the explanation to play at a later date, then of course you'll be able to do that through the YouTube channel. Thank you, Kieran. Yes, me too as well. I must admit, certainly here in the UK, it's been a tough 3 months so far since the lockdown began in January. But there are signs that things are starting to ease again now. So I'm hoping for first trips now. I've had the first dose of the vaccine to begin in April as well. So for sure, I look forward to catching up with you again soon, Kieran. And thanks for watching as well. Appreciate it. Oh, Michael, you're staying up really late for us. Thank you so much. We appreciate that. And at least now, because you've had 40 minutes of listening to me, you should be able to sleep quite easily tonight, I would imagine. So, okay, any final questions? Last call for any questions. And then we will close the webinar, and you should get a follow-up email from us within the next couple of hours with all the contact details that we discussed on there, and some opportunities to reach out to us outside of the webinar as well if there's any questions that should come to mind afterwards. So all that remains from our side is to say thank you to all of you for joining us today on this webinar. We really appreciate the time that you've taken to spend with us today on our very first webinar as well. Please do reach out to us if there's any topics that you'd like us to cover in future releases or future volumes. And if you even liked it, or I mean, you can even feel free to say, please don't make any more. We can't sit through those as well. So any criticism or praise is always greatly received. But from my side, I'd personally like to thank everybody in Eurovent who spent so much time putting together the the documentations and certain things like that we've used through reading and putting together this webinar, and also the people at Riva for the good guidance that we've constantly had through this difficult situation, this pandemic situation. Just a last quick question from Michael. Differential pressure guidance in rotary and plate heat exchanger as additionally. Yeah, we can send some details across to you, Michael. We've got all your contact details, so we'll jump out of the webinar at some point and we'll come back to you separately. If you're in South Korea, it'll be Eric Tan as well, who will come back to you. He's been with Heatex a long time, so he's a very good guy as well. Yes, Thao, we can send the document. And thank you, Jesper. Really appreciate it, and thanks for joining us as well. And hopefully soon at the next show, we can try to grab a couple of cold beers as well. So, okay, thank you everybody for attending today. We really appreciate the time, and we look forward to seeing you on the next one.
Thank you.